Good afternoon, everyone. So my name is, as you can see, Patrice, which is hard to pronounce for English people, I know. And I work at both Université de Sherbrooke and Collège Leroux in Quebec. I do a number of things. I have kids, as you can see. I have animals in significant amount. Now, I'm known to be a very bad slide organizer. There are some artists in this place. I'm not one of them. I'm a chalkboard person. But I decided to do something this year. I put cat pictures. Sure, I put cat pictures because my wife has a refuge. And she has these cats these strays that we get, we sterilize and find families for. This is probably not the best venue to show cats off, but still, I decided to do something useful. So she exists, you will see cat pictures for good reasons, not just for distraction. I've been teaching since 1998. I've done flight simulators. I'm on the C++ standards committee and a number of other things, and that's about it. I do way too much stuff. I put in the slides, but mostly for your own pleasure, should you download them, a number of tools that I often use when I give presentations, but I won't be using them much today. I'll have a few links though. But I invite you to check them out. We have a tooling group in C++ these days. SG15 is working hard at making the life of everyone easier and make sure that what goes into namespace std and what is peripheral but useful both find their ways to you. These are other things. These are tools that are online and can help you demonstrate things that are interesting. So the number of online compilers, the online help, that's almost standard there. There's a shell there. There's an online Clang. There's Godbolt. That's absolutely awesome. That you've probably seen in many talks if you've been to CppCon before or this year. I won't be using him much today, but he's awesome. He's going to be here this week, I know. There's the text of the standard that's more than up to date, that's generated from the current sources all the time that you can actually check. That's C++ draft there, that's awesome. There's the benchmark tool by Fred Tingo, who's somewhere in the conference. I saw him a few times this week. The core guidelines, and so forth, and so on. I urge you to get acquainted with these tools because they're very good, and none of them is by me, and I'm not taking any money. Just, they're good tools, and they give, I think, the language a well-deserved good reputation. So, as I said, I have cat pictures. They're not all for sale, be careful, not all for gift. These two stay at home, but it was a nice picture anyway. So some of you might have come here because of the title, some of you have come here because of the abstract. Why am I giving this talk? Well, it's a study I had earlier this year, saying, well, normally, and I know something about that because I work with the games people, and I'm in SG14 for the low latency people, we tend to write programs because we want them to go fast. And people often associate C++ with going fast. Chandler talked about this a few years back, Chandler Carruth, and he reminded us, I think it was in this very room, that it's not speed that C++ gives us, it's control. And through control, we tend to make things go fast, or be small, or what have you. But yeah, we tend to be very happy. We show people that we generate less machine code, we can bolt it. We run benchmark and say, oh, my code is fast. It's cool, but sometimes it's useful to make programs in such ways that the worst case scenario is fast, that you're predictable, that you have a low average deviation, and for these things, C++ is an awesome language too. So I'm not focusing on the fast side of things today, I'm focusing on something else. So if you want to leave, now's the time. I'm going to try to look into ways of making the worst case less bad. Which will not be good for your code in general unless you want that thing to happen. So you might get lesser performance, but you will be fast when it counts. But that's the point here. But it's a beautiful language for that because it gives you control. That's the point. We're trying to look into such techniques. Tell the compiler things in such a way that the compiler does what we want, but the compiler is good. So it's not a matter of saying, the compiler, I know better than you how to optimize my code. Just, if you optimize the code the way everybody wants it to be optimized, you're not going to serve me. So please listen to me, more in that sense. Because the compiler is right. It's going to get a better result than you are. And I was asked to say that this is probably intermediate, not too advanced, but maybe not beginners also. If it's beginners, just write to me and I'll write back. Yeah, and if you're wondering why we should do such things, or why sometimes it's important to worry about the worst case. So that's the point. So then, why? So this one is called Peter. It went out of our house a few times and came back, and came out and came back, because every time we find a family, there's some issue, like it mewed, and we were not sure what to do about it. Or the kids were sick, so it's the cat's fault. Nice cat. So I put a link there where, with all of the examples that I put in the slides, the examples in the slides are incomplete, but the code there compiles, and you should probably be able to run it on any compiler that you care for. These are auto examples, they are to show techniques. Yeah, that's it. So not everyone worries about worst case behavior, of course, because that's not what we talk about normally. Most of you, I guess, when you're running benchmarks, you're looking at throughput, you're looking at the best case, average case maybe, or something. There are people, though, for whom worst case is significantly worrying. Those that have life-saving devices, where you normally don't stop that seesaw, but when you have to stop it, it has to stop right away because there are arms along the way. Where you have a self-driving car, and when you press on the brake, well, you normally don't press on the brake. When you press on the brake, it would be better if it braked. Think of that. You steer your airplane, and it would be nice if it answered. And there are programs that have to be stable. Like, just minimize, as I said, average deviation to make sure that from iteration to iteration you get pretty much the same results, the same load. And you're always playing with, if you get more of this, you're gonna get less of that. So if that's what you want to optimize for, compiler might not be doing that by default. So as an example, I work with people sometimes who are looking to get as many frames per second on screen as they can. 70, 75, 80, awesome. But if it's not stable, it's unpleasant. I don't know if you've ever worn those casks on your head where there's a display there for the Oculus Rift and stuff. I used to do military flight simulators where you're inside the aircraft. And if the sound and the pictures are not stable and according to the expectations of your body, you puke. And within 15 to 20 minutes, and someone has to clean up. And that someone sometimes is someone who writes programs. And it's unpleasant. So sometimes it's better to have less pictures per second, but have them at a very, very stable rate, or to have a very fluid audio because your ears are not happy when it's not. And your ears tend to play havoc in your equilibrium or your state of mind. So the trick is to use the CPU for intelligent purposes, though. So yeah, exceptions have a bad reputation, but they're not that bad. So I have this example that I put on screen right away. I don't know if it's big enough for people. No, you don't see it because it's on the wrong screen. So there we go. I thought it was on the right one. There, and make it bigger. Can we see something? Yeah, we can. So I wrote this small thing just for fun. Because there's this exception with on line 10, it's called darn because it's a very significant name, of course, good naming. And there's two functions there. One that's called f, that if it gets a number that's above 0, returns a negative, and otherwise complains. And there's the other one called g, that if it gets a positive number, returns a negative one, like the other one, and returns an empty optional should there be a problem, to signal that something went wrong or whatever, because I guess it's not expecting that. And two functions that generate nice data, like all negatives, all positives, and nasty data that generate all negatives. So best case, worst case, something like that. And a test function that, if you don't know how to read it, just measures the time it takes to run something and reports it in some measurement unit. You can then convert with Howard Innant's amazing tools. And I run this thing 1 million times or so. And I count the number of successes and failures in both cases. And I have one that checks with exceptions if something failed, and the other one that checks with the optional if it failed. So an if statement and an exception like that. And they both treat both the good case and the bad case. So one of them never fails, and one of them fails all the time. So you see, exceptions get a bad rep because people say, well, it's slow and it's bad, and it's fat. Well, it's not bad at all. In fact, for the best case, it's not that bad at all. In this one, it's pretty stable though. Depending on run, sometimes we get it even faster than up shuttle, depends on the cases. When I ran it on my computer the first time, I got better numbers for the best case with exceptions than I get with the up shuttle in that one, and it's happened quite a few times. But the worst case is terrible. I don't know if you see that. So exceptions are made for the exceptional case. So when the exceptions occur all the time, you're into a very bad situation. You pick the wrong way to handle the problem. But if it never fails or so, it's actually pretty good. So if you're worried about throughput, about speed, you might want to use exceptions in this case. Maybe the numbers I got when I ran the thing the first few times, because they're good for you. But if that time when you don't want it to happen, it occurs, and then you fail your timings and something bad happens, it's really not cool. So the best choice for performance might not be the best choice for you in that case. Yeah, because they're actually faster sometimes. Yeah, so this is what I said. What if you have react fast? Let's say you have a container, something like this other one there, which is kind of similar, testing time again. I'm doing pushbacks and inserts at the beginning, depending on the cases, with a vector in the deck. Now everyone will say, of course, vector will lose this race, because you're inserting at the beginning sometimes, and vector is terrible for that. It's not meant for that, of course. Whereas deck has been made precisely for this sort of thing. No? If you don't believe me, try it. The numbers are awesome. So if you run something like this, of course you expect vector to fail because of the number of push fronts, essentially, and inserts at the beginning. Because the pushbacks, the vector would win all the time. And it's true. I mean, the numbers are terrible for vector if you look at it. But even with the reserve, I mean, the issue is that it's moving stuff all the time. If you're inserting at the beginning, you get terrible numbers. Still. I took it with just pushbacks. Vectors, of course, trash deck directly if I did that. But then, what do you pick? I mean, if you think you're always going to insert at the end, use vector. If you're always inserting at the beginning, use deck. But if you're not sure, and if it's bad for you, if you take too much time, now that becomes a bit more annoying, because you're going to get more stable performances probably with deck than with vector if you always, well, either one or the other, it's going to work well. But with vector at the end, it's going to be awesome. At the beginning, it's going to be terrible. So you're going to get a huge variation if you play with both. If you know your case, you're okay. So yeah, so if you're concerned about the worst case, maybe deck would be best in this case. But that's not what we tell people, of course, because on average, vector will trash everyone. So it's not a matter of being the fastest, it's a matter of being fast enough. Or not being too slow, which is kind of the same thing. So, it's not British. There are real cats that need love. Now, so people say, well, synthetic benchmarks. Blah. So let's go driving. The sources are on the shared drive if you want to look at them. Oops, that's not what I want to do. This is what I want to do. So this is ridiculous. Okay, I know cars don't drive themselves in straight lines. Okay. Shh. Mind you, I have kids, and I've seen it happen. My car has marks for that. So there's this exception case up there calling collision risk detected. And there's this drive thing that takes a direction and checks if there's nothing along the way, and if there's something along the way, it says, ah! Otherwise it just keeps on going in a straight line. That's not a self-driving car, and no, I know you won't hire me for that, that's okay. But then a bit later, there's this function that queries destination, computes the direction, and then while I'm going there, driving towards the destination, and if something happens, like this, because you breathe when that happens. So if you have a good driver, well, and low collision risks, that might seem good. I mean, you're not really going to crash, then you're going to be to behave properly, say, or something. But if time is of the essence when you detect a risk of collision, well, this implementation, as we could see earlier, it's not the best one, maybe, because you might have a bit of a higher delay in reaction, probably not that big in terms of speed at which a computer runs with respect to the speed at which a car runs, but it's just a picture, of course. You know that in this case, you might have worst case behavior, and it might not be what you want. Again. It does look good, doesn't it? And sometimes what you want is something more constant. You want a throughput that's stable, more than fast or slow. So something that is almost the same in all cases. So I wrote this thing that your no return, the function cannot exit through a return, but can exit through an exception if something bad happens. So there's this loop there that has a data of some kind, tries to read from it. It's blocking I/O in this case, and tries to process the data as it comes in. And in the extremely rare case, let's say, where something bad happens, you cannot consume, well, you throw something like this, which is the right way of processing the error in this case. Well, you will be reacting very fast to the incoming of data. If it comes in and you're ready, it unblocks and you react right away. And if it doesn't come, well, you're waiting, and you're wasting your time, you're not doing anything useful. Some people say it's perfect. I mean, you want to react right away when something happens. But if you want something that is stable and you want to pursue some other tasks, well, you're wasteful. It really depends on what you're doing. You're wasteful in the sense that you could be using time for something else. But yeah, you're reacting immediately something happens, so it's efficient in a way. But you can be blocked for a long time. Yeah. So if your data arrives at a constant rate, this could be pretty cool. But otherwise, it might be nasty. So if you rewrite the thing this way, just an infinite loop, and if you get something blocking, you process some data, and otherwise you throw something, well, and again, it's the same loop as before. I mean, you're expecting to fail only in very extreme cases. You can see that you're not processing the data at a stable rate in this case if the I/O is blocking. So if you want to do something like this, trying to read and then perform some accessory tasks, well, they wouldn't be performed at a stable rate. It would be performed whenever you got something, and if nothing comes in, you're going to wait for a long time in these tasks. They will wait. Might not be bad, depends on what you're doing. So yeah, we can't predict the rate at which we'll be able to do the thing in this case. Yeah, which is annoying. And it might never be called, in fact. So if you need to do them and nothing comes in with code like this, you're kind of stuck, which is not cool. Now, if you rewrite it this way, with something that does non-blocking I/O, try to consume of sorts, that would, let's say, return an optional data of some kind, well, you can ensure that if you don't get anything, you're selective in doing something, and presuming that your try consume takes a stable amount of time, you can have predictable behavior, but overall, you're going to be using CPU power, so it's only useful if you're doing something useful, of course. But you're active. You're always doing the accessory tasks at, we can presume, a stable rate if everything well goes fine. And if something really, really bad happens, well, you're still throwing and leaving, but in the meantime, you're active. So should this be what you need to do, you can do it. That's maybe not the reflex that everyone would have. Yeah. So you can be sure that this will be done all the time. And if there's a bound on the time it requires to perform process data, well, you can offer some guarantees, because you control the code. This is presumed, at least. This often occurs also with event-driven code and polling code. I'm finishing my PhD these days, and a number of people I've worked with in the last 10 years, because it's taken forever, are very much event-driven people and say, this is good, this spares bandwidth, this is optimal. Well, it's optimal. Yeah, it is. It means that you're not doing anything if you don't need to. It also means you have no control over the rate at which you're doing things, and that if the events come in as bursts, we're going to have peaks and lows, which can be okay. If that's not what you want, well, it's a bad model. It really depends on what you want to do. Or you can pile up things and do something hybrid, but anyway. So I wrote this thing there that you might see above. There's something called next event that returns an optional that might be empty. There's nothing. And there's a location where we register functions that react to events. Is that to call thing up there? There's a mutex because it's a very poor man's synchronized queue. And there's something to subscribe, add something to react to the events, something called callback, which reacts and just goes through the loop and say, hey, reacts to events. And there's that execute thing that waits for an event, and if there's something to do, calls back. So it's active, it's playing things like that. And when something happens, there's a burst and everyone reacts. So if you get many events in a short period of time, you're going to be very active. Otherwise, well, you'll just be idle. You can do it this way also. So I have this shared pointer there called reg. That's a shared registry. And I can subscribe a few events to that, the function, lambda, say. Then I start a thread, then the thread runs, and I detach it, oh, go and react to events. Go forth and multiply or something. So it seems efficient because, well, you get something, you react. Otherwise, you poll. You're only calling back if something useful has happened. Otherwise, you're not calling back the function. So if you're going through the network with your callbacks, well, you're not wasting with the network resources. You have nothing to do. And there's moments where nothing happens, and there's moments where you work a lot. So as long as you don't have anything planned for those moments because you're going to be swamped with work, you're okay. But if you're looking for low average deviation, this is not doing what you want, really. Because when you're doing a lot of work, well, you're not responsive, and maybe there's something else you should be doing at the same time, and well, that won't happen in time, in that case. So if you're playing with polling, well, polling is seen as bad because you're always checking for things all the time. Maybe for nothing, but it gives you control. It gives you control over the rate. So if this is what you want, of course, because I'm saying, do polling. I'm saying, whoa, there are reasons sometimes to do it. Let's take a breather. So it's easy to confuse, like, generally better, always better, never do it. And confusing these things might be dangerous. So seen otherwise, there's this thing there to call, vector functions that will call back again. A function that reacts to an event, a lambda, whatever. So some storage that takes the functions. And then I use the deck in this case. And a position in the deck, so I'm iterating through it, and then coming up again and again. And if there's an event, it's being pushed to the things in the list of things to process. And later on, there's a phase where, well, where there's still time to do something and there's something to do, well, we call whatever function we're up to, and otherwise, and then when you've treated everything we had to treat, well, we pop up the thing, and we restart over again with the next one. So we have control over the number of functions we're calling in a given time. And if there's no time left, we can stop and come again and pursue where we were before that. We get control. More complex, I agree. I know that blocking for a cycle like I'm doing down there is a bad idea. I know it's bad form, but it gives you control. You can also switch the things like I did in this slide and say, well, I'm going to first ensure that I can do things. And if there's still time left after that, I'm going to consume from the network tasks to do, and then go back again. So the moment in my cycle when I start to do processing will always be the same, essentially. Instead of being at an elastic place in the cycle, depending on how much processing I did before. So depending on what you do, it might be more stable there. If you were trying to display pictures on screen, say, you're going to display at a specific moment in the cycle instead of at a variable moment in the cycle. It's going to feel better to your eyes and to your heart. And you can even do it with 2 threads if you want. Something like this. So there's one thread up there that's consuming and adding to a, let's hope, synchronized queue of sorts. And one that's processing and saying, well, forever, while there's still time to do things, if there's something to do, I do it, then I move to the next one. And when I've processed everyone, well, I take the next one and I continue, as long as I have time, of course, to do things. And then I stop. The thing is perfect. The thing is possible. So polling tends to be less efficient, of course. It consumes cycles that you don't really need to consume sometimes, but you control your rate. So it's not something that you should throw away, just something that you might not consider in general, but that's something you should never consider ever. Something different. Bursts in processing, sometimes they're just that. Depends on what you do. There are things that have to be stable, like a pacemaker. It's preferable if it works at a stable rate. I'm more used to things that play with audio and video, but there are things that actually keep you alive sometimes. So we have tools in C++ to help you to do things like that. And this one is called Helen. She's very, very sweet, but I haven't touched her in 3 years. She doesn't like humans, but she's the mother of many of the cats that we have. At some point, we're going to be able to cut her nails. So the first rule first. I was talking with Andrew Pardo earlier this year and told me there are things at DAC that you shouldn't show to people because they're bad. They're trying to tell the compiler how to do the job. No. The compiler does a very good job. The compiler writers are very good. They're awesome people. Let them do their job. But in some cases, you want to be more precise as to what you want. That's something different, because the assumption that they make might not be the same as that you make. So optimization is something that's complex. You don't just optimize for something, you measure, as Howard would tell you. If you don't measure, you're wasting your time, literally. And sometimes you want to optimize for non-obvious reasons. Like, the average case is not the one that's critical. Sometimes that's what happens. And sometimes, well, it's the average case that you want to keep within a small range. So things that we have. Some people do log programming and things like that. They can use atomics. It's going to give you a lot of control, but it's dangerous if you're doing that and you don't know what you're doing. A number of functions of the try style. I was using a try get or try consume or whatever. There's try lock on the mutexes that lets you do non-blocking tentatives of getting a mutex and work along with it. You're not blocked when you're doing that, so you can control the rate, the throughput of what you're doing. Those that I know who do real-time audio, they use that all the time. It keeps their audio feed alive and their jobs active, because otherwise they would be losing them. We have trilocks on trilocks on things such as Uniclock. We have trilog 4, trilog until. You have a lot of control with C++ for that. Things like scope lock guard, they don't give you that kind of control too. You just block until you get things. So you have to look at the right tools. There's an example there that's very, very simple, where there's a vector of data and some kind of big deck of data up there, and there's a loop that tries to receive data, put it in the local buffer that's V. So V is a temporary storage, let's say, for something that will at some point be moved to the deck up there. It's called data. And it tries to log the mutex. But if it doesn't, it keeps on piling in the local variable, because somebody else may be trying to use the data up there. And at some point, after a while, manages to get the lock, well, tries to move whatever data was acquired along the way to the deck and didn't then clear and continue like that. So it doesn't have to block until the deck is free. You can just try, and at some point, when nobody else is bothering, move it there and that's okay. I know. So if we did just lock, we wouldn't have that kind of control over what we're doing. The thing that don't block, I know that some people are advocating never block for good reasons. Well, at some point we'll have the .then in futures, which would be pretty nice to be able to chain things and not block. That's not really what we're talking about, but still. We have a number of time wait functions in language, wait for, wait until. So you can control how much time you're willing to wait before it becomes a problem, and then go down doing something else. You can even just poke 0 milliseconds, why not? There's a small example there where you're trying to lock something for a little while, trying yeah, that's it. Trying to wait for an event. If it doesn't come, well, you're doing something else. And at some point, you go back to your main task, and you again try, then you stop, whatever. And someday, someone will signal the event, and then you do something. But you're not blocked. I use optional for a few examples. That's pretty nice. So sometimes, instead of having an exception, which is very good in general, but sometimes very bad, because something that's stable, and what it costs you is if statements. It'd be annoying, but still. Raw pointers work too, but memory management becomes painful with it. So optional is cool. There's one there, a very, very cheap concurrent queue, please. This is not a concurrent queue example. With a deck inside, a mutex, and someone tries to add, well, if it works, you get a true. If it doesn't work, you get a false. It's okay. And there's a try lock in there that tries to get the mutex, and should it work, makes it adopt by a log guard inside with the new syntax. It's very nice, the CTAD, and then it plays back and return true. So this thing kind of works. It doesn't work. It doesn't block. If you do not manage to insert the thing, you can just remember that you have to do it some later time, and it's going to work. You're not blocked in the meantime. You control your time. This one is not exception safe. It's a version of extract, try extract, that is, do you see why it's not exception safe? I wouldn't use this one because you might be losing some critical information like credit card data, money, children. Do you see why it's not exception safe, this one? It's a thing of evil, isn't it? Yep. No, because there's a log guard, so it will be. What's the problem? If there's a log guard, it's going to get killed at some point. What's the problem? It's a well-known problem. Sorry? Yeah, if you have a throw along the way, if you have a throw when you're returning, the outside world will never see what you return in this case. So that's a bit of a line. You say your optional will not throw. Well, yeah, the T that's copied inside might. So depending on what you're doing, this would be nicer in this situation. You pass a TREF inside. You try to write to this one, and if the write has worked, the rest of the code that follows it will not throw any exceptions, and you're pretty safe. So there are ways to write this kind of code. But see, you can do this without blocking, and you're risking any leak or something. It works. So it's a bit more complex, maybe, but still. Of course, if you have nothing to do, you just block. No? But if you have things to do, if you need the time, if you need stability, then. There's other things. These two. I saw the author of these in the room earlier today. I don't know if it's either here or right now, Clay. These are the ones that made Mr. Pardo react when I was talking to him. He says, this is like register all over again. You know that register keyword everyone loves? I heard that this morning again in the keynote. Like the registers in the interface. Yeah, right. Don't use register, of course. The compiler knows better. So people say, well, you're telling the compiler which branch of your if statements are going to be taken. The compiler knows best. Of course, the compiler knows best. I know that. That's not the point. The point is sometimes the compiler knows what's the best case and what's the average case and what will get you the best results, but that's not what you want. Sometimes you want the pathway that you'll never take to be optimized because when you go there, it's really, really, really important that you're very fast. It's more for that kind of stuff. You know, if you're trying to make sure that the thing that will not be optimized for good reasons is optimized for because you're willing to take the performance hit because you have reason for that, then it's interesting. It's not lying to the compiler. Of course, use them nicely. If you use them for something that makes no sense, you just degenerate the performance. It's pointless. But if you say, well, I know that the if is more likely, but optimize for the else, I have my reasons, there you go. So please don't try to outguess the compiler. This feature is interesting in the sense that if you look at the standard text, it's, I think, one of the rare ones, if not the only one, where the warning sign saying don't use this is bigger than the actual description of the feature. And I see compiler people moving their heads like there. But yeah, don't use it, but there are reasons for that. And so it's when the optimizations are unintuitive, when only you know things that escape from the source code, that's not written in the code, but you have outside knowledge that might guide things. Yeah, so we should see that very little. That's so. Yeah.
May I add one comment?
Please.
Go back and revisit. If you add those to your code, go back and revisit them at least once a month because they go stale very, very fast.
Yeah. See, if you try to outguess the compiler, as Justin was saying, you're probably losing. But what I have in mind here is the case where you know it's bad, but still that's what you know. And as he's saying, assumptions like that, since they make your code go slower, you should check them out from time to time because, yeah, staleness in code is not a good thing. So I'm not trying to say people use that all the time. No way. But they are there for a reason. And probably not for the reason people expect. What we don't want, I count myself in there, is people saying, I'm going to put this everywhere because I'm such a hotshot. You're going to lose your job. So this is a ridiculous example where someone is saying, well, I'm using an exception throwing API to slow my car if there's a problem. And for some weird reason, because that's really not the best API in this case, I know that the cache is a bad idea, but please optimize the cache because I know I'm going to get into trouble. If I go there, I'm not fast enough. This, of course, you won't do that for self-driving car. It's an example. Okay? If you're having an exceptional case like this, an if statement would be better. But if it's your API, you're stuck with it, use it. Okay? So this would make your performance go down. It's a very, very bad idea. But should you find yourself in such a situation, that's the tool for you. I hope nobody will tell me that they did this and it made their program slower because I know. Okay, so by definition, you shouldn't get there in the first place. But, you know, when that happens, I feel like blood's falling out of my arms when I'm showing things like that. There's also this is my cat. There's also the case where you'd have too much computation time to do for the budget that you have. There's a competition that my students try to do sometimes of AI for a well-known game where they are trying to write a planner for the game to throw enemies at one another but they have a short amount of time to do so, and then they get kicked out. And they're wondering, since they have too much computation to do in the time that they have, how they can manage still to make decisions instead of just butching and rolling dice. That's a typical case. So one trick that I gave them was write small functions. And then they look at you with like, serious small functions, what a novel idea. Because some people feel bad about short functions, they get the impression that they're not doing anything. Because, oh, it's so small, please. More than 2 lines, write another one, please. But what you can do is divide your computation into smaller steps, of course. And do the steps, and at some point stop, then start when you stop. This is old school. Don't do that on modern computers, okay? Don't. But it used to work. I've done that in the past, but way in the past. I haven't done that in the next 20 years, except as examples. There's this function there with a static variable, not thread safe and everything, that remembers where the code stopped last time. So it starts at some point the first time, and then when you call it, it remembers that place it went. So there's no breaks between the cases. It's moving along, and occasionally it checks, should I stop? Is my time budget exceeded? And if it says so, well, you're exiting a function, of course. And when you're called again, because of the switch, you jump to the beginning of the last step you did not complete, and you pursue. Now, this is not good for modern computers and modern code, but this step thing, very C-like, used to be a thing, and shows my age. And if you're more modern and still not perfect, this is slightly better because the state is being passed along by the client code, so you don't have to rely on a low local state that's shared by every thread that's passing by. But it's the same idea. I'm using the fall through there to tell the compiler to please shut up because I didn't put a break. Be polite with your compiler, of course. But do you see the point? Yeah, so this might be a way to do things. It's old school a bit. When I showed that the last time I gave this talk, somebody said, what about this new, shh, it's coming. If you want to tell me about something else, it's coming. One way to use things like that is to take a function like the classic transform here that's probably not as nice looking as the one your current provider is giving you because I haven't optimized it at all, and make it so that it can remember where it stopped last time, and you can restart it from the point where you stopped the last time and control the way it stops. So do a transform or a for each or whatever, but in short steps with a condition to make it stop at some point, like this one. It's more complex. So I don't know if you see this one. It's returning a pair with the new features again, the CTED, that's cute. And it takes 5 arguments in this case, the beginning of the source, the end of the source, the beginning of the destination, the function to apply, and some predicate that you will evaluate as you go along. And it's moving along, but checking the predicate occasionally. Now I'm checking at every iteration. That's a choice I made. And if there's still a reason to continue in this case, then you continue. Otherwise, you return where you stopped. You return where you stopped reading and where you stopped writing, such that you can continue from that point on. Next time, somebody else calls you, whatever. So you add a small budget of time. You don't have control over what you're doing, really. So you're trying to do something. At some point, the time is exceeded. Well, just store wherever you stopped. And continue next time. The caller has to remember the state of that stopping point, but the code has to be written accordingly. Lambdas are cool for that. So there's this very small example there, where there's this process, this function f that processes data and returns processed data. There's that now function up there that returns the current time. That's because the slides are not big enough to take the whole system clock colon now thing. If there's only one thing that I don't like about short ones, the length of the names. But they make sense. And there's that make pred there that returns a lambda that takes now and then adds some moment and returns true if you hadn't exceeded the deadline, something like that. So a bit lower down, you're gathering data. There's some location to put the process data at some point. And you're trying to process as much as you can. And then until you've done, you could be doing something else in the meantime, of course, otherwise why do it that way? But you're doing some auxiliary tasks. And then you're restarting where you stopped, and so on and so forth. So why would you do something like that? Well, as I was saying, it could be stopped by some external force. You could be trying to achieve one picture on screen every so often at a very stable rate, and preparing, you display the current picture, you prepare the next one, and there's still some time left. You're wondering, what should I do with that time? Well, you could make some other computation progress, such that you have less to do later on, because you have time. So use it. But of course, you don't want to exceed your time budget. So you give yourself a way to measure the time that's left. You leave yourself in this little room just in case you would be tight, because you want your pictures to be there at a very stable rate. And when you sleep or when you suspend or whatever, wait for the next iteration, well, you do it less because you've done something useful in the meantime. You don't do that if you have nothing to do. You do that if there's something to do in the meantime. And then overall, you might get better overall performance because you've prepared things along the way that you won't have to prepare as a batch later on. Some of the old games that my students and now the professional gaming people do, they used to have long pauses in between levels because they were preparing stuff that they will display to you. That's awful. You don't want to get it. You don't want to wait for a display screen and say, hey, wait for me for a minute or two and then I'll come back and play the game. So if you're preparing stuff in the meantime, you're waiting less. You have happy customers, you're rich, you buy a Ferrari, whatever. Or something such. But that's bad. But people say, you're doing more work. You're doing more work. You're wasting computing cycles or something. You could be more efficient by doing a straight transform. Be doing more operations in the same period of time because you're not adding the overhead of checking the time all the time. You're right. It's a different use case. You're going to get better throughput. Maybe if you're compressing data, say, piecemeal like that, you might have better compression rates if you're doing it all at once. But yeah, depends on what you're doing. If you want to make things progress a bit in the meantime and use your time to the fullest, maybe it's something you're going to do. They can be used in many things. They can be used in critical tasks, of course. When you have something like this, you know, you have the critical task, and then something that's accessory. Well, you want the accessory thing not to exceed your time budget because then it might be dangerous. So there. This is the kind of planning situation I was talking about the game, where you have your frame rate, you're displaying your scene, you're preparing the next one. This thing tends to be stable, preparing elastic, and you have some long-term planning to do to make sure that you will be also more interesting in the game after that, and the monsters will be fun, and they will scare you and things, but that takes time. And if you've seen the games people, they put all of their time and energy on what you see, not on the way the creatures will group together to make your life more complicated, that they do in the spare time that they have left sometimes. So that's an interesting way of preparing things in the meantime. Of course, today you do that with coroutines. If we have them, but they're coming. I don't know if they're coming for 20, I hope, but they're coming soon because it's a complex issue. But still, if you're about to separate the things into little steps, we do have a feature in C++ that's coming for that. It's called coroutines. Coroutines make for very nice line code. I mean, you can subdivide things, stop at some point, and when you call it again, you restart from where you stopped. It's just natural, and it's supported by the language. You let the client code control the granularity if you want, and the state is being managed underneath the covers. So it's nice. They're resumable functions. They have implicitly managed state in between calls. That's cool. And it's a hopeful for C++ 20. We'll know in San Diego in a month or two where I won't be. I'm going to miss this one. So this is a very simple example, just with odd numbers or even numbers. I don't remember, even integers. But it's a function that would return vectors of integers that have been generated since last call when you stop it. And you pass it a predicate, in this case, to tell it, well, I'd like you to stop after a while because I have other things to do and I will have enough even integers for a while. So the vector is there, I'm piling up data inside. And at some point when I decide that I've had enough, when the if statement makes it so the predicate is not met, then I enter and I yield. I yield the vector in the state where it was and I return it to the client code, which will consume the even integers. And when I'm called back again, I'm clearing the vector, I'm continuing piling stuff in there. So I'm doing some asynchronous tasks, really, computations that might be more useful than even integers for whomever is calling me, which will be like consumed at some point. And from the caller's point of view, it's simple too. The only thing to manage in this case is having a predicate that does the right thing, meaning that it stops at the right moment. And in this case, I made a fixed amount. I think it's 500 microseconds or so. I put a small deadline. So I'm consuming even integers, stopping displaying them, and then making some others generate, so I can be doing something else in the meantime. This is nicer and much less manual than the other techniques. Lightweight, supported by the language, cute. So coming to a C++ compiler near you very soon. Is that okay? I heard a duck. Is that okay? I have this thing, but I also have bonus slides. Look at the pause of this cat. Okay. So just because I wanted to make it shorter to just get a bit further, just something that's associated with that. That's not the same thing, but that I found fun myself. This is my wife's cat. So imagine a situation where you want to do something like, this is simple, you want to compare two simple C-style strings and return true if they're identical. In the case, this is very simple. I'm just taking the two strings like that and comparing them. Like, in a very simplified way, what you do when you enter a password in a card somewhere and you're wondering, like, do I have the right password or something? You're comparing two bits of data. And there's this system solution there that says, well, if they're not null, well, if one of them is null, I'm returning something. Otherwise, well, I'm going through a sequence until I hit the end. And as soon as I find a character in the sequence that's not the same, hey, I leave because I have an answer. And when we're optimizing code, that's what we do. We try to leave as soon as we have the solution. Say, hey, why should I stay there? I found it. Now, from some perspectives, this is very bad because you're leaking information, aren't you? If somebody is very mean and measuring the time it takes to call your function with a hidden bit of data that they don't know about and some test set that they have, they might be like playing mastermind with you and trying to divine how close they are to finding the actual code. And they might be measuring the time and say, oh, this one lasted a bit longer than the previous ones, so I must be getting closer or something. So this is bad. It's bad from that point of view, because if you're hostile, that the timing of that thing leaks information. What you would like it to do, I think, if you're from a security standpoint or something, you would like the time it takes to compute this function to be strictly dependent on the size of the input. Be simpler. So, yeah. There was a paper for that in 2014 that never got anywhere because I think the problem interests nobody else than me. It's not my paper, it was from someone else. And if I may quote, it says, one of the hardest challenges when implementing cryptographic functionality with well-defined mathematical properties is to avoid side channel attacks. That is, breaches exploiting physical effects dependent on secret data. Such effects include variances in timing of execution, power consumption, blah, blah, blah. C++ does not consider such effects as part of the observable behavior of the machine, thereby allowing implementations to vary these properties in unspecified ways, which is a reality. We don't specify these things. We don't talk about timing in the abstract machine. That's not what we do. So what the paper called the data invariant function would be one that tells the compiler, you know, this one, it's really important that the time's always the same. So don't try to do optimizations that would break this property that we're trying to achieve to have very predictable runtime behavior. Not fast, not slow. Exactly what I asked for. If you optimize, you're not helping me. Please don't. This is a weird talk, I know. So it's an interesting challenge because if you look at this is like the basic one I have. Of course, it leaks timing information because it stops as soon as it can. So when I'm with students, I say, okay, let's make this one data invariant, they try things. And we look out. So all that's coming is from people I work with, students that are very intelligent and trying things. So first of all, you need to change your API a bit to be sure that it's a simpler problem, because otherwise we'll be going to all sorts of details that we don't care about. So arguments of fixed length, which could be some kind of preprocessing, such that when you arrive at your function, that you're okay. Or you make sure that you always go up to a certain length, if it's the length of the longest one, that's more complex or something. But we'll make it simple, something like this. So I have a size t there, that's the number of characters I'm checking. And both strings are presumed to be the same size. This one leaks. This one leaks. Do you see that? For the same reason as before, meaning that as soon as I have something, I get out. So that's bad. It's just the reflex that we have. I would normally leave as soon as I can from a function. Why should I continue on the input? Why? No, I have my answer, but this is not the use case again. So it's an early return. That's bad. For this, this is another one. Some people say, well, then don't return. Take a Boolean. And assign to it as soon as you have your answer, but keep it inside. But it still leaks. Do you see why? But for bridge prediction, we would need that feature that says don't do it. But in this case, bridge prediction, I can control it. But this one, well, I can. This one thing is you can count the number of times you went into if statements, and you know things about that. You know how close in terms of quantitative number, how many times you put false in a variable, if you can measure it, and if you have a very dumb optimization level. So you can see things. This is also tempting, saying, well, then I don't have an if statement. But you can do, don't you? You cannot do, yeah, because depending on the value of the first argument of the ampersand thing there, well, you're going to do the second part more or less often. So this still leaks something. So it's not a trivial matter. You have to think about it a bit. You see that? Yeah. So it's difficult to be stable. How about this one? Is this one nicer? It probably is. It probably is because it probably does always the same kind of computation. If if the compiler listens to you, it doesn't optimize, and if there's things there too, because there's no branching or whatever. It's doing some equal thing. You can cast that to an int, so you have 1 or 0, and you do a bitwise AND there. At some point, you're going to get a number, but you're doing this the exact same number of times every time you're counting. So yeah, so it's a tricky problem, but it's interesting in the perspective of what we're discussing today, which is trying to have stable speed instead of the best speed possible. Making sense? And maybe I have. What have I done? That's totally a typo. Thank you. I will fix it. Thank you. And there might be typos in the other ones too, because I didn't. That's a reflex. So there's a typo that will be fixed in the final version. You should be able to pick from this weird depot where we put the slides. Any other questions or comments? Threats? No? Okay. So these functions are interesting. It's a nice exercise and it's fun to do. And that's about it for today. Questions? Comments? If not, you can have a nice afternoon. Thank you.